when we study simple harmonic motion, we come to the realization that it's not very realistic. So as you're swinging back and forth, and so the truth is that there is obviously friction which gets involved. So if you have a pendulum, if you have a spring and a mass, so it's not going to just go bobble back and forth forever, perpetually. So we run into something which is called damped harmonic motion. Now the word damped just really is referring to friction. So if you're talking about damped harmonic motion, you can think back of simple harmonic motion, which is a nice oscillating periodic back and forth. But now if you're going to add friction into it, it's not going to just simply bobble back and forth forever. And we have really three forms of damped motion that you do study in kind of physics as you're going along. So in short, damped harmonic motion is nothing else but periodic motion, but it is affected by friction. And it may not look periodic at all, as you will see shortly. Now, friction, don't forget, is nothing else but the transition of the energy. And that transitioning is going to go through heat, and then it's going to dissipate into thermal energy as you have. So if you're thinking about the law of conservation, which you maybe have studied, so if you have, as you have the equation right here for mechanical energy, so you might be thinking about kinetic energy, all right, check mark, gravitational potential energy, check mark. Then you started to, as you alluded into springs, to talk about elastic potential energy. So you can add all of these together, and you can do certainly examples. You can put up an example right there for you, where you have transfers of energy. But when you bring in friction, so this other energies that we have, well, one of them might be thermal energy that you are going to incorporate, and that's what friction will do. So if you see there on the right hand side, if you have a pendulum, well, that pendulum, depending on how damped it is, so it might swing back, okay, and forth, back and forth, and then it's going to slowly lose its amplitude until eventually it's going to settle within its equilibrium. So if it does that, if it starts to swing back and forth just like a simple harmonic motion, however, the amplitude is going to get decreased because of the fact that you have friction, then that would be kind of the first type of damped motion. And that is called under damped motion. So in these situations, as you can see here, I'm going to highlight, so it is a system which oscillates back and forth around an equilibrium. So like a pendulum, like a spring, which goes back and forth, or many others. However, it gradually comes to rest. So as you can see there, so it's going to swing back and forth, but it's going to gradually come to a rest. So that is under damped motion. Where do you have these? Well, you have a swinging pendulum, so that's one example. You have a swinging mass, which goes back and forth, okay, with regards to a spring, or something a little bit more realistic, which is a bouncing car suspension, which you maybe have gotten used to. Now, if that suspension is not the greatest, okay, as you have, it might swing you back and forth, which is not really what you want. Okay, however, okay, that swinging back and forth on that suspension as you're going through eventually does settle down. So those are some examples. Now, the amount of the actual damped motion that you carry is rather low. So because of the fact that you're still swinging or still, damping or bouncing as the car in the springs, okay, or in the suspension, so the actual damping isn't enormous. So the amount of friction is still there, but you're still kind of bobbing back and forth. So the system, it loses or at least transfers energy, but it does it so slowly, right? Or at least slowly relative to some other damped motions, right? So your damped level of under damped motion, okay, is rather slow, where it's going back and forth within here. So and then it eventually does oscillate through, okay, and then it settles. The second type of damped motion is critically damped motion. So what is critically damped motion? Well, so as you can see there within the definition on the screen, so critically damped motion is a system which returns to an equilibrium, but it does it quickly, okay, as quickly as possible, but without oscillating. So if you have a pendulum, right? So if it's kind of going in and you start to swing it, it doesn't overshoot and then come back and then come back and then slowly settle. That's underdamped. But what happens is it shoots back very quickly, but then it's really kind of slows back down. Okay, so it shoots very quickly and then gets to the equilibrium, but it doesn't overshoot the equilibrium. So in these types of examples, you might see this in an automatic door closer, right? So if you have an automatic door closer, okay, that smoothly and quickly shuts the door without slamming it or bouncing it back. So some cars, you might be able to kind of go in. Now, if they're just mechanical cars, it will probably slam. But if they have some kind of a dampener, you might close it. It might go very quickly, but then, okay, it will nicely shut in instead of bouncing back within there. So the amount of damping level is actually kind of the optimal amount of damping. And the system returns to rest in the shortest time without any overshoot, any oscillations at all. So it does it very quickly, but it doesn't overshoot. The last one, which is overdamped motion. So in here, a system returns to an equilibrium, but it does it rather slowly and without also no oscillating. So again, if it's a pendulum, it would just kind of like slowly try to return back to an equilibrium. Okay, so that would be overdamped. So the word over is because it just really, there's a lot of friction, so it doesn't allow it to come back very quickly like it would in a critically damped where it does it very quickly. So here, you might see these in very heavy door, okay, openers that you have and then closing. So you don't want the door to be slamming at you if you're walking through the door. And sometimes if the damper is broken, that's what happens. You'll pull the door, and then as you're walking through, it just shuts right behind you. That would be, okay, kind of pulling you in. But if you have an overdamped motion, okay, system, then it won't shut down very quickly. It's going to give you the time to actually walk through the door, and then it's slowly going to return back to its equilibrium. So that amount of damping is actually very high, and the system is overly resistant, okay, to motion. So it doesn't want to do it very quickly, and it takes a pretty long time to come back, and it does not oscillate through. Now, if you think back of simple harmonic motion, right? So if we were to graph these simple harmonic motions, so the graph of a simple harmonic motion would look something like this. This is kind of like in perpetuity, okay? So it just goes on forever, where you have a certain amplitude and then it swings back and then it goes back in. Now again, please remember the time, okay, is on the x-axis, and then the displacement that you have with respect to some equilibrium is on the y-axis in here. So this is just showing you what is happening relative to time. So it's just kind of swinging back and forth. So if you had a pendulum, so this would have been swinging, okay, back and forth forever. It would not dampen at all. So now if you take the simple harmonic motion and you bring in friction, then you start having these types of graphs. And so now let's talk about these types of graphs and what they represent in terms. Again, time is on the x-axis, and on the y-axis, it is the actual displacement relative to an equilibrium. So if you were starting far away, so if you had your pendulum, okay, and you kind of started to swing it back, so let's say it's kind of swung at 1, so as you see there on the graph at the top, so it starts at 1, and then you let it go, so it will swing over. Now if it swings over, but it doesn't get back to -1, so at least on the other side, because that would be simple harmonic motion if it's swinging back and forth and it's the same displacement. But if it swings back, it doesn't go as high, and then it returns again not as high, not as high, not as high, and then it dampens down. So that is what you see right here, okay, with this one. So it starts off, swings over on the other side, but notice, okay, so it doesn't go to -1, and then it swings back, again, doesn't go as high, and so it oscillates back and forth as you're going through and eventually settles. So this one is referred to as, okay, underdamped. So this is your underdamped that you have. Now, the next one that we talked about was critically damped. So critically damped meant that you would swing back to your equilibrium very quickly. You wouldn't overshoot, right? So you don't oscillate at all, but you do it very quickly as you're going through. So this, okay, is an example of a critically, okay, damped motion where it happens very, very quickly, right? So with respect to time. So notice that in just a couple of seconds, it's almost right back, and almost by 6 seconds, it's pretty much back to its original equilibrium. And then the last one, which happens very slowly, this is over-damped. And then over-damped, just as you can see, it doesn't oscillate, right? It doesn't swing back, but it's slowly, it's kind of like that door, which is shutting down behind you. So a heavy door, but it's doing it very slowly. So that is over-damped. And that's how these graphs would look like, all right? So those are the 3 types of damped motion caused by friction within systems. And now, so just to summarize, okay, for us, so the summary is underdamped, okay, so it oscillates multiple times before stopping, like a swinging pendulum or like a mass on a spring. Critically damped, it returns to rest very quickly without oscillating at all. Overdamped, it returns to rest slowly without oscillating. So those are the 3 that you have. Thanks for watching. We'll see you in a future video. Bye, everybody.